All right, everyone. Thanks again for coming to the last day of this workshop. So what we will do today is switch gears a bit. So we have covered the basics of what probabilistic circuits are. And really the first 2 days we set up the context by giving you what generative models look like and what are the things that you expect from a generative model in terms of reasoning capabilities and if existing deep models can do that. And we saw that not many of the deep generative models can do probabilistic reasoning efficiently. And then we built this class of probabilistic circuits, and we saw how certain inference queries can be computed tractably, right? Now what we'll do today is move slightly ahead. We'll see how people have improved these probabilistic circuits to make them more deep, more expressive, almost to the level where they are getting to be competitive with neural models, right? So we'll discuss what people have done to bridge the gap between these tractable probabilistic circuits and deep generative models. Sorry, I think I'm moving a lot. I was told not to move. Sorry. We'll also, so what we'll do is I'll introduce a class of models called normalizing flows. If you remember from yesterday's talk, we briefly touched upon normalizing flows, which was a class of deep generative models, right? And we'll see how you can sort of borrow concepts from deep generative models and probabilistic circuits to build hybrid models that are both expressive and tractable. We'll have some hands-on demo as well in between, right? And finally, I'll introduce you to some of the cool applications that these deep tractable probabilistic models can have in downstream applications. And then we'll sort of wrap it up and conclude. Yep, sounds good. Okay, so just to ensure that you haven't forgotten what we discussed yesterday, this is sort of the the diagram of a probabilistic circuit that we built yesterday, right? So you're interested in modeling a joint distribution, and the way we sort of formulated this was starting from some simple distributions and then passing it through a computational graph to model something more complex. Now, what does this computational graph look like? It consists of three types of nodes, right? So you have simple leaf distributions. You have some nodes which represent mixtures and adds expressivity to your model, and you have product nodes that encode factorizations and makes things tractable, right? All right. So the first three parts we covered until yesterday. We saw how you represent distributions using PCs, how does inference become tractable on PCs, and also to some extent, how do you learn these PCs, right? Now today we'll start with how you can make these representations more expressive, more deep, and in a way that is similar to your tensorized neural networks, so that it's easily deployable on GPUs and you can train them at scale. Okay, so where we stopped at yesterday specifically in the learning of PCs was in structured learning, right? So we were making this argument that so you have both parameters and structures in a PC, right? And you can learn both of them from data, and we saw how you do parameter learning and how you can do structured learning, but it was more heuristic based, right? But what happens when you do structured learning? So you have a computational graph, and if you're learning the structure of this computational graph from your data, what can happen at times is that this graph can be very sparse. And when you have a computational graph that is very sparse and you want to scale it to say millions of parameters and like large amounts of data, then such a representation is not very easily deployable or parallelizable and deployable on GPUs, right? So you need denser computational graph if you really want to use the power of modern GPUs. So the question is, okay, how do you get to a denser representation? Because if you are going to learn these structures, then you do not have any sort of homogeneous tensorized view of this, right? So how do you build such a view? Okay, well, so one of the most interesting papers for me that came out in 2020 was called Random Tensorized Sum Product Networks. So the view they took was that, okay, structured learning might be important in certain domains, especially when you have fewer amounts of data, right? But in many domains where you have a large amount of data, learning the structure explicitly might not be very, very important. What you can instead do is assume that you have a large number of randomly generated structure for your computational graph, right? When you have such a large ensemble of random structures, then such a model can be almost as expressive and equivalent to having a learned structure, right? So the point is, when you have a sufficiently large ensemble of random structures, it performs as well as a learned structure. This is something people have like observed even before in classical machine learning as well, where you have things like random forests, etc. Right? So the notion of having random structures was first explored in 2017 in the context of what are called cut-set networks, but then they were made more deep and adapted to the class of like just smooth and decomposable circuits like we discussed yesterday in 2020. So how do you build these random structured tensorized probabilistic circuits? Well, to understand this, I'll first define the notion of what is called a region graph. Now, if you visualize what happens in a PC, what you're really doing is to gain tractability, you are sort of decomposing how your joint distribution is modeled using your product nodes by having factorizations into something simpler, right? So you're really defining how this joint set of variables decomposes as you move from the root node to the leaf nodes. So let's sort of define that a priori, even without looking at a PC. Let's define how you want to decompose these variables, and that is what a region graph gives you, right? So you start with all the variables. Let me get the pen. Okay. So you start, let's say you have 9 variables, right? And at the root node, you are interested in modeling a distribution over these 9 variables. Now, as you move down in the PC, when you have product nodes, you are sort of dividing these into disjoint subsets, right? And you will model distributions over these disjoint subsets. Well, you can sort of construct this in advance, right? So what you can do is, okay, start with all the 9 variables here, and then I have 2 types of nodes in this graph. One is the region node, which just represents the set of variables over which I'm computing a distribution over, and then you have partition nodes, which are similar to having a product node, which partitions the subsets of variables into 2 disjoint sets, right? So when I pass this 9 variables through a partition node, what I'm really doing is I'm randomly splitting these sets of variables into 2, right? So okay, in this case, I'm saying these sets of variables, the one on the top right goes to my right child, and the remaining goes to my left child, right? So you're randomly selecting which random variables gets decomposed at a product node by just randomly sampling these variables, right? So you keep on doing this. So you start with all the variables at a region node at the root level. You have a partition node that splits it into 2, right? And this is sort of giving you the structure for your probabilistic circuit itself, right? Because what does the structure say? It gives you how your variables are sort of decomposed and how you are building them together. So if you have such a notion of a region graph, which is a random region graph per se, actually, because you are randomly splitting the variables into disjoint subsets, then you can convert this region graph representation into a probabilistic circuit very easily. Okay? So this is how, if you're trying to visualize how would this look like if you are doing something like an image data distribution, right? So you have at the root level you have all the pixels, right? And then when you pass it through a partition node, you're sort of randomly splitting these sets of pixels into 2. In this case, you can have more. So let's say this partition node splits my entire image into 2, which is one is this and the other one is this, right? So similarly, you can have randomly arbitrarily defined partitions, right? And then what you're really doing, trying to do is to build a huge mixture model that works at each of these sub levels and then combine them together using this computational graph, right? Make sense? Okay. Okay. So I said that you can like randomly split these pixels or split these random variables, but here it's not so random, right? We have some additional inductive bias, right? Here we are splitting in an axis aligned way, because that makes more sense for images, because when you have pixels that are close by, it's more likely that they are like more related to each other, right? So there's this spatial correlation in images that you can account for when you're doing the splitting, right? But if it was like tabular data, you wouldn't really mind. You would just randomly sample which variables go to your left or right child, right? So this is how you do the splitting and get, we haven't reached the PC yet. What we have so far done is just define a decomposition for your entire set of variables into something simpler, right? Now we still need to convert this representation into a probabilistic circuit, and that is what a random tensorized sum product network, or in short RAD-SPN, does, right? So this is what we had. We had an entire set of variables, we had region nodes, and then we had partition nodes, and we kept on going until we like reached leaf levels where we had some subsets of variables, right? Now to convert this representation into a PC, all you have to do is equip each of these nodes in your region graphs with sums and products. Now how do you do that? So at the leaf level, what you really have is random variables, some subsets of random variables, and you have to define what do you define at the leaves? You define simple tractable distributions, right? So I can have something like Gaussians defined at the leaf level. Now if I go one step up, where I'm looking at a partition node, so let's call this depth, or let's call this what do we call this? Yeah, let's call this. So this is h equals 0, h equals 1, right? So at height equals 1, I have partition nodes. What do partition nodes do? They split the variables into two disjoint subsets, and that is very similar to what a product node does, right? So to convert the region graph into a PC at a partition node level, what you do is equip the partition node with product nodes. So this was your partition node. Now what you do is equip it with this product nodes that computes a product of the distribution at the leaf level, right? Good? All right. Now, when you keep on going, when you reach a region node at a level higher than the partition node, what you would do is equip it with some nodes, and you keep on doing this until you reach the root, right? Because we saw yesterday that the way you built a probabilistic circuit is you have alternating sums and products. Good. So in short, you equip the leaf regions with vectorized versions of leaf distributions, right? So you have a vector that represents probability over, say, k different distributions over a given variable, and then at a higher level you compute products over these vectorized leaf inputs, and then at a region level, what you do is you take summations, right? So you vectorize everything. You have vectorized leaves, vectorized products, and vectorized sum units. So this results in a vectorized PC that is smooth, decomposable, and it's also very easy to over-parameterize this and scale on GPUs, right? Because now you have more like a homogeneous structure. Your leaves can only be at the lowest level, right? They are all at the same level, and all nodes at a particular level are of the same type. So you have all product nodes at, say, height 1, all sum nodes at height 2, and so on and so forth, which means you have a more homogeneous structure, and which is also computationally dense. It's easy to deploy this on GPUs. And how would you over-parameterize such a model? How do you increase the expressivity of this model? Well, you can define how many summations to take and how many leaf nodes do you need, right? So here I have chosen just 2 sum nodes, but I can increase this. I can say, okay, I'm going to use 100 sum nodes at a level, right? So that's an easy way. All you would be doing, if you think in terms of vectorized computations, is increasing the dimension along some axis, right? That's all you're doing, and that results in a lot more parameters. So you have a vectorized way that is easy to over-parameterize and train. So that was the idea. Yeah. Right. So if you remember, so smoothness, what is smoothness? Smoothness is basically says that your sum node should be defined over the same scope, right? Good. And the way we constructed a region graph is you're assigning, so the way you constructed a PC from a region graph is you're assigning sum nodes to the region nodes. And all the sum nodes in the region nodes have the same scope, because that is how you define the PC itself, right? So if you look at the region graph, let me say, go back, right? So you're adding a sum node here, and at this level, you're looking at a set of pixels, which is the same for both the child, right? This is the same for each region node, which means smoothness is guaranteed by construction. Now, if you look at the partition nodes, which is where you're adding the product nodes, the way you are partitioning is, so the way you are splitting the random variables is in such a way that they result in disjoint partitions, right? And that is exactly what you need for decomposability, right? What you need is you do not have overlapping subsets of variables.
But you're not testing for that, the independence. You're constructing it. You're forcing the
right.
So
Right.
that's the caveat that I want to bring up.
Yeah, right.
It's the design that choices that
right.
you make that it makes it a smooth and decomposable.
Right. Right.
It's
Right.
not the other way. It's not from the statistical properties of
Right.
from the data. You're not inferring it from data. You're enforcing it through the construction of the conditions.
Right. Right. Yep, yep. No, that's like a very good point, right? I did not think of like explaining that. So like he said, right, when you learn, you are sort of looking at these independencies from like as being present in the data, and then you are enforcing this through a product node. But in this representation, you are a priori defining this structure, right? So these independencies might not really hold, right, because you have these random structures, and when you're randomly sampling, the independencies that they lead to might not be present in your data distribution, which means you might have lower expressivity. But the whole point is it's okay if you have one such structure, but if you keep on adding a lot of such random structures, the expectation is that it counters for that reduction, right? So you have, when you have a sufficiently large ensemble of such random structures, then it becomes expressive enough, right? That's the whole point. Okay, good. Any questions here? Yeah. So if you think of this computational graph, so in a normal, like if you do structured learning in a PC, you can have like a PC that goes, let me see if I can draw something. You can have computational graphs that are very long, which do not have a large number of connected components, right? But the way you are constructing here, you have vectorized some nodes at a layer, you have vectorized product nodes at the second layer, and everything is connected to everything, right? So everything in a product node at a product level is connected to all the sum nodes at the higher level, right? And you are not allowing for variables to mix at any arbitrary depth, but they can only mix at the leaf level, right? Right. So in this case, let me call this a depth 1, 2, 3, 4. So all the variables, you have it at the same depth, right? But you don't really have such a constraint when you're just doing structured learning for PCs. You can have these input variables coming in at arbitrary depth, which means you cannot do everything parallelly, because you'll have to compute it like bottom up, right? So some variables might have to be computed before you'll have some sort of ordering. But here you can do everything parallelly. You can like do all these products operations independently and parallelize it on GPU, right? You can perform the entire forward pass at a particular level by deploying them on GPU, which is not possible when you have a sparser graph, which is of a non-homogeneous shape. Make sense? Right, right, exactly. This structure is something you're defining, right? So this is a random, so the structure here is in terms of, okay, what is the structure? The structure is in terms of how the variables are being split. That is actually what the structure is in a PC, right? And you are sort of randomly defining how are your subsets coming out to be, right, by randomly sampling. So you are sort of fixing a random structure in this case. But now you can take an ensemble. So this is in a 2D plane, right? Now I can do the splitting again for say 100 times. All I'm doing is in a vectorized sense, I'm just adding another dimension to my tensor, right? And then I can allow everything to mix at the root level, because at the root level everything would be defined over all your random variables, right? So the point is this representation is very easy to scale, right? So you can now take say mixtures of such PCs very easily, right? So and each element of this mixture, so each 2D structure would have like the independencies would be drawn randomly, like there is some sort of stochasticity. But when you take a sufficiently large ensemble, that doesn't really matter. Your parameter learning sorts of covers up for it, because you have a large number of parameters, you can over parameterize, right? So, and you can learn it easily from data if you have sufficient data. Cool. Okay. So if you look at this representation, there's something like some more things you can do to improve the efficiency here. So you have these two different types of operations, right? You have some vectorized product operations that are happening, and you have some vectorized sum operations that are happening. I haven't put the weights here, but you do know that there are parameters associated with the sum nodes, right? Those are what you would learn. So this idea of having random tensorized sum product networks was further extended to what are called einsum networks, which we saw yesterday in the demo very briefly, I did not mention that these are deep PCs, and I did not explain how they work yesterday. But borrowing from like what we just discussed about RAD SPNs or random tensorized SPNs, if you look at these computational graph layers, you have products and sums, and but if you look at neural models, you have a slightly cleaner version where you have like you can stack the same sort of layer arbitrarily many times, right? So you can stack like linear layers arbitrarily many times. But here you need to stack like different types of layers. Can you do something better? Can you do something better to improve how these computations are done and to make things much more cleaner and efficient? That is the idea of using the Einstein notation here. So, and what results is called an Einstein network, right? So you can combine the operation of doing products and then taking a summation over these products into a single operation, which is called an Einstein operation, right? So a single Einstein operation, what it does is it takes an outer product and it sums the values in the product along a particular direction by weighing it with a weight, right? So if you have these are two distributions n and n prime, all you're really doing is you're taking a product, an outer product, and then you're sort of vectorizing this outer product out and taking a weighted combination. That is what really happens if you think of what happens at two layers, right? If you think of two layers together, that's what happens. You're taking a product, and then you're taking a summation over some dimensions of this product. Now, this entire thing can be very, very compactly and very efficiently notated and computed using what is called the Einstein operation, where you define which indices of your tensors are being multiplied and which indices are being summed over, right? And most libraries, most like deep learning libraries that support backpropagation also have an efficient way of implementing this Einstein operation, right? So, question? Yeah, so you can combine the sums and products into what is called a single Einstein operation with a 3D weight tensor. That's the whole point. And so when you do this, what you see is that you have, instead of having multiple or like two different types of operations, sum, products, and sums, you now have one single homogeneous, think of it like a neural network layer, right, that does this sum product operation, right, in a single Einstein, like reduces it to what we call as an Einstein operator. So you can combine all such operations at the same depth into a huge layer, which is similar to what you have in a neural network layer. And if you are taking a graph view of the computational graph, right, you can order these layers topologically using breadth first search, which means you now have something very similar to a neural network, right? So you have a set of layers that goes from your input to the output, right? And in a PC, it's more from your leaf layer to your root layer, right? So you stack such multiple layers like a neural network, and then you can easily learn them using backpropagation from your data, right? So to summarize, all the operations in a layer can be computed parallelly. Before you had sums and products that had to be done in a different way, but now with the Einstein notation, you can do all the operations parallelly in a single step. You can also now replicate or like create multiple replicas of PCs. What do I mean by that? So we saw that in the 2D version of your region graph and the vectorized conversion of it into a PC. We were doing these computations in a 2D space, right? So you had something like a 2D vector, but now I can take multiple such representations and combine them into an even huge mixture by just adding another dimension to my tensor. All I have to do is specify which elements, which indices in this tensors are being multiplied and which are being added, right? So it's easy to over-parameterize this model, and this was probably one of the like approaches that scaled PCs to the level that they could model image distributions over data sets like celeb A and the SVHN. Right, so the resulting like Einstein notation and the Einstein operation resulted in up to 2 orders of magnitude faster computations, and it allowed scaling PCs to higher dimensional data sets which were previously not possible. Right? Yeah. Mm-hmm. Right. So most libraries support doing the Einstein operation very efficiently. No, it was there before, but no one had like sort of combining the sum and product operations into an Einstein operation. It's more like an engineering hack, I would say, but it resulted in a lot of like easier way to like scale things up.
So can we use that Einstein normal complex combinations for products and samples?
Right, right, right. You can use that. So it's an easier way of specifying when you have tensorized computations, right? When you have tensorized computations and you are interested in taking products over certain dimensions and summing over certain dimensions, the Einstein notation gives you an easy way of doing it. All you have to do is specify which indices are getting summed over and which indices are getting multiplied, right? So, and most libraries support specifying the ANSUM operation. Yeah. All right. Okay. So let me like go back to what where we started from, right? We started from the classical generative models, classical Markov networks, Bayesian networks, and we said that they are not so expressive. And then we talked about some deep models, and saw that they're expressive, but then they cannot do probabilistic reasoning, right? And what we're really interested in is bridging the gap between these models, because there's no free lunch. So if you really want tractability for a probabilistic inference, you'll have to make some structural assumptions, you'll have to give up some level of expressivity, right? And if expressivity is all you need, then you won't be having any capability for doing probabilistic reasoning and inference tractably, right? So you have this dichotomy of models on the expressivity tractability spectrum, where you have deep models on the expressive side and models like the tractable probabilistic models on the other side, and all the works that we have like discussed so far have been in like taking these tractable models and making them more expressive, right? But if you still look at the landscape, you'll see, and if you look at the sort of samples that these models generate, you'll see that there's still a huge gap between the expressivity of these models. So even Einstein networks do not generate samples which are of like comparable fidelity and quality with what deeper models generate, right? So the question like we will ask, and this is what I work mostly on my research, is how do you bridge this gap between the expressivity and tractability part of the spectrum, right? So, and the key idea is that if you analyze what is going on, so models on the right end of the spectrum are all deep models. They are using neural networks in some way as flexible function approximators to gain that expressivity, right? And models on the left end of the spectrum, they focus on incorporating some level of structure through independencies, through factorizations, to make probabilistic inference tractable, right? So how do you borrow concepts from both ends of the spectrum, right? And can you build hybrid models that incorporate both to achieve best of both expressivity and tractability? That is sort of the research question that we will try to like understand in the next 40 minutes or so, right? All right. So, well, to do that, let's do one thing. So let's look at the spectrum and see what is the most expressive, what is an expressive model that is most tractable here. It is a normalizing flow, right? We saw yesterday that a normalizing flow can do evidential inference exactly. We'll come to that again. And let's consider a probabilistic circuit, a deep version of a probabilistic circuit, something like an Einstein network, which is a tractable model, but which is one of the most expressive model on the tractable end of the spectrum, right? And let's see if you can combine inductive biases from both of these models to construct some hybrid models, which we will call probabilistic flow circuits. But before that, let me give you a slight introduction to normalizing flows, because I assume most of you might not be familiar with normalizing flows. So let's see what a normalizing flow actually looks like, right? So this is a slide what we saw yesterday, where we are interested in building a deep generative model, use neural networks in some way to learn a data distribution. And what we saw yesterday was that, okay, if you have some structure over a neural model, not some structure, you need the model to be invertible. If you have an invertible model, then you can sort of transform data sample from a simple Gaussian or noise space into the data space and back. And you can use what is called the change of variables formula to link the probability densities in these two spaces, right? And then use maximum likelihood to learn the entire model. This was like the high level picture I gave you yesterday. Let's sort of go into a bit more depth today, what a normalizing flow looks like, right? So what you do is, okay, you have this complex distribution in your data space, right? It could be anything. It could be over images, over text, over like tabular features, anything. But there is this high dimensional complex distribution, the shape of which you do not know, right? But now if I were to tell you, okay, there is some transformation, I do not know what the transformation is, there is some way I can warp this space in which your data lies, so that I can slowly convert this into something that looks like a Gaussian. Right? So I'm starting with my data space here. I'm applying some transformation to change it slightly at different parts until it looks like something like a Gaussian. Now, if you can do that, I'm not telling you how you do that, or if you can actually do that, but just imagine you can do that, right? If you can do that, then you can sort of formulate the generative process very easily, because and you also need that these transformations to be invertible. If you have such a transformation that moves your data space into something that looks like a Gaussian, and this transformation is invertible, then how do you generate new samples? All you have to do is generate samples from this simple Gaussian space, and then keep on doing the inverse transformation of whatever you apply it until you reach the data space, right? So does the intuition make clear? How does having invertibility help for such a transformation? Yeah.
Somehow related to certain limit theory. Gosh, we have multiple.
That's a good question, right? You can think of it, but here you do not have. You're transforming the same random variable through a sequence of transformations, right? In central limit theorem, you have a large number of variables, right? And you're saying that as they increase, your joint distribution looks something like a Gaussian, right? It could be linked. I haven't thought in depth, but good question. Like, we can maybe look at it. But this is a common theme.
So an equal impression of that is how is it related to variational inference?
Variational inference. So here you're not doing variational inference. Here you have an exact way of computing the likelihood, right? Variational inference comes in where, okay, so think of it like this.
Maybe put it this way. These transformations are approximate. Or
Right.
exact.
Right, right,
And you have the invertible functions. That
Right.
are also equally approximate. Then is this just doing variational inference?
Yes, yes. So if I were to take these two transformations, right? So I have the forward transformation and I have the inverse transformation, right? And if I do not have a transformation that is invertible, but I can have an approximation for my forward transformation, I can train an inverse transformation which is approximate, then it becomes sort of similar to having variational inference, like what you do in a VAE, right? In a VAE, you are looking at the posterior over Z given X, and you are assuming that it has some parametric shape, and you are using a neural model to learn that, right? So you are sort of posing the problem of inference as an optimization problem, which is what variational inference does. But here, you really don't need to do that, because you are already assuming that your functions are invertible, which means you can go back and forth exactly, right? And you don't have to make any sort of approximations. But the point is, like, exactly like spot on, that if your functions are not invertible and if you have to make approximations, then it is sort of like doing variational inference if you're looking at any one of the directions.
And sorry, one important point is for mainly for the students. Sorry.
Yep, thank you. Right, so if you have such an invertible, please.
So why do we always shoot for a Gaussian distribution? I think what would be going on.
Yeah, so you don't have, the base distribution doesn't have to be Gaussian, right? You can assume any distribution in your latent space, but the thing is, you need something that is easy to sample from, and what you know the PDF for, right? So you should know what the probability density is in that space. So you have some analytical way of computing the density in the latent space. So it could be anything simple. You can have other like distributions as well.
But is there research going on studying?
Yeah, so people have looked at using like different base distributions, but the point is it really doesn't matter, because if you have, so we'll see that these invertible transformations are actually neural transformations, right? So having a more complex distribution at the base level is almost equivalent to having an additional neural transformation that transforms it into something simpler, right? So in that sense, if you have sufficient depth or sufficiently many such transformations, then the structure of your base distribution doesn't really make any significant impact. Makes sense? Okay. All right. So what I was saying is, if you have a way of transforming this space using a function that is invertible into something simpler, then you can do generation by sampling in the simple space and then applying the inverse transformation. Now, the good thing about invertible functions is that they are closed under compositions, right? So when you take compositions of functions that are bijective, you still get a bijective transformation, right? So what you can do is, instead of learning this entire complex invertible transformation, I can break it down into simpler steps where I make like small changes to my data distribution using a transformation, and then I keep on doing this. So each of these small change is by an invertible transformation, but then I compose this with similar transformations sufficiently, and the entire process is still invertible because inversions are closed under composition, right? So you parameterize this entire thing. Ideally, what you would like to do is parameterize this, find a way to parameterize an invertible transformation using a neural network, right, and then learn it from data. Okay, now what all things can you do here? When you think of from a generative modeling perspective, obviously you can do sampling. All you have to do is sample in the Gaussian space and apply the inverse transformation. You can also do evidential inference here. Why? That is coming in from the change of variables formula. So what the change of variables formula tells you is that if you wanna find out what the density associated with, say, a data point here is, well, what I can do is I can look at what the density associated with that data point is in the Gaussian space. Let's say that when I apply this complex transformation, my space warps in such a way that this data point here gets transformed to something here. And if you have an inverse transformation, you have a unique mapping, right? So for every element in this data space, you have a unique z value, and it's vice versa, right? You have 1, 1 and 1 on 2. That is what an invertible mapping is, right? So you have that uniqueness, which means you can uniquely identify a data point by a unique latent feature, right? So I can look at what the probability density, to compute what the probability density associated with a particular data point in my data space is. The change of variables formula tells me that, okay, all you have to do is look at what the density for that data point is in the corresponding simple Gaussian space. I can do this because I know what the PDF of a Gaussian looks like. I can directly compute it analytically, but then that is not the density itself, because this transformation resulted in your space expanding or contracting in some way, right? So you have to multiply the density with a term which is the determinant. So I'm putting it in a very technical way. It is called the determinant. It's a determinant of your Jacobian matrix. So the Jacobian is the derivative of this transformation with respect to your inputs. But an intuitive way of thinking about the determinant of a Jacobian is how much does the volume change at a particular point, right? When you're applying a transformation, you're really expanding at a point or like contracting at a point, right? So and that changes the probability density, right? So all the change of variables formula says is that it links the density in the data space with the Gaussian space, and there's a volume correction term that accounts for how much your transformation warped this entire space, right? That's like at a very high level. Good? Clear? Okay. Now the good thing with these normalizing flows is that there's a way to parameterize them in a neural network like architecture, which means they are more expressive than probabilistic circuits, but they are also tractable to some extent, right? Because you can do evidential inference. You still cannot do more complex queries like marginals or conditionals. There's no way you can. There's at least, research is going on in how to make them more tractable. But as of now, you cannot perform integrations or do marginalizations on a normalizing flow, right? So the question then is, can you combine both? But before that, let me give you some more idea into normalizing flows. So here are some results. So you might be wondering, okay, if you really need tractability, you might have to make a lot of structural assumptions, which means these models might not be so expressive. But what you see is these are like data distributions in like a million dimensional space. I think this is 1024 cross 1024 images, right? And a normalizing flow is very good at generating approximating distributions, complex distributions in this high dimensional space. It's almost as good as like what VAEs and GANs can generate. So not all of these spaces are generated by a normalizing flow, right? They are not of real people. But the point is they are more tractable, right? Okay, so this is something I discussed. So this is how the normalizing flow formulates the problem of density estimation. And the key property is that if you were to build such a transformation, there are a couple of things that you'll have to additionally keep in mind here, right? So you need these functions to be first invertible. And second, if you really want to apply the change of variables formula, which involves a Jacobian term, Now the Jacobian is, you can think of it as a partial derivative, right? So you need these functions to be differentiable. So you need them to be invertible, which means they are, in mathematical terms, you call them homeomorphisms. You also need them to be differentiable. Now, you call such transformations diffeomorphisms. Now, in addition, you also need a third thing, which is that you should have a way of computing this Jacobian determinant in an efficient way. Because if you have a transformation f that transforms x into z, and you want the function to be invertible, what should be the dimension in both spaces? If I have d dimensions here, and I want the function to be invertible, I cannot have a dimension that is smaller than d here, right? Because then I'll lose information. I do not have a one-to-one map. Now, if I look at what the Jacobian of such a transformation would be, I'm computing the partial derivative of every element here with respect to every input. So you will have a d cross d matrix, right, as the Jacobian. Now, that is still not enough, because you'll have to compute the determinant of this d cross d matrix, which means it will take you order of d cube time to compute this determinant. And if you have like high dimensional data, like images with like 1 million pixels, right, this blows up very fast, right? You cannot do these computations very easily. So you need to design transformations that has these three properties. They should be invertible, they should be differentiable, and you should show that their Jacobian determinants are easily computable. And designing such functions is really the core research problem in the field of normalizing flows. Good. Now, many of you might be wondering, why are they called normalizing flows? Well, it's simple. If you think of the distribution, a complex distribution, and you're applying these invertible transformations, you can sort of think of the distribution as flowing in through a pipe into something more simpler, right? And typically you have a normal distribution at the end as base distribution, which is why you typically call them normalizing flows, right? So you can slowly flow a complex distribution step by step into a normal distribution. Yep. And let me show you what a real example like on a synthetic data looks like. So let's say I'm starting with a complex, this is something you would have seen, the two-moon distribution, right? Now, if I were to use an invertible transformation to transform this into a Gaussian, this is how it would look like. So as I move through each single transformation in this entire sequence, my data space is being like extended. It's contracting or expanding in such a way that at the end you have something that looks like a normal. Make sense? I'm referring to this particular thing here. And since it is invertible, you have a way of mapping it again back to your data distribution. Now, how do you train these models? Well, I can just do maximum likelihood, because I can do evidential inference tractably. I start with a data point. I process it through the sequence of transformations until I reach the Gaussian space, right? And then I can compute what the likelihood associated with that data point is using the change of variables formula. Assuming that I can do all these computations very efficiently, then all I have to do is do backpropagation and train the model to maximize this likelihood, right? Now, what are the parameters here? The parameters here would be the parameters associated with each of these transformations. And I haven't defined what these transformations are. I have just told you that assume that there exists a transformation that is invertible. Good. And it should also be differentiable. Then you can solve it using gradient descent. So what are these models tractable for? Again, you can do sampling by sampling in the Gaussian space and applying the inverse transformation. You can do density estimation by using the change of variables formula. But you cannot do things like marginals, conditionals, or map because you do not have a way of decomposing integrals like we saw yesterday in this particular class of models, right? Okay, so now you might be wondering, I have told you that there exist some flow transformations which are invertible, but how do you design transformations that are invertible but also expressive, right? Well, maybe something that comes to your mind quickly if you are someone who works with neural models is the feed-forward layer, right? A simple linear transformation. Can you have a linear transformation that is invertible? Well, yes, but you'll have to ensure that. So when you have a linear transformation, it's more like you can think of it as multiplying it with a matrix, right? But if you want the transformation to be invertible, you'll have to ensure that the matrix is invertible, which is a hard task if you also want to learn the matrix. So it's more like a constraint optimization problem where you want to where you want to learn a matrix, right, which defines the transformation, but you also want that matrix to be invertible, to have all its eigenvalues to be like positive or non-zero, right? So ensuring that achieving invertibility during learning for linear flows is hard, and even the computation of determinant is d cubed. There's nothing efficient here, so you need something better. You wanna have something that is more expressive. And another point I will add is that when you apply a linear transformation over a Gaussian, so an affine transform Gaussian is still a Gaussian, right? You're not having any additional, you're not having anything more expressive than a Gaussian if you were to simply apply an affine transformation. So you need something more expressive, something that has a Jacobian determinant that is more easily computable and that is invertible, easy to invert, right? So one of these cool, smart ideas that came up to solve this problem was called coupling-based transformations, right? And I found this particularly like very cool, and I was like mind blown when I saw that you know how you could design an invertible transformation in such a simple way, right? So I will walk you through one particular instance of how you do this parameterization. Like there are a lot of ways in which people have proposed a lot of new ways in which you can build such invertible transformations. But just to give you an idea of like a flavor of like how this looks like in the context of neural models, I'll look at what are called coupling flows, right? So what you do is you really want to learn a transformation. Let me call this F that transforms your X into Z such that it is also easy to invert. Now, what you can do is, okay, I'm going to split my data into two parts. Okay, wait, so let me actually do this. So you have your data X. What I'm going to do is I'm going to split this into two halves, let's say XA and XB. I'm just going to copy the first half into my output. Now, the first half, I'm also going to use it as input to a neural model that outputs me some parameters, and I'm going to use the parameters outputted by this neural model to transform the second half of my input in a very simple way, right? And I'm going to define the output as just the concatenation of these two output vectors. So if you look at it, I'm starting from X, I'm dividing it into 2. I'm just copying the first half in my output, but the second half I'm modifying it as a function conditioned on my first half. Does that make sense? Now, I haven't told you what this coupling network is, what is this transformation that you're applying, but at a high level, this is what you do. Now, we'll see how this becomes tractable or like invertible, right? And the whole point is to come up with some simple transformation. Let's say, in this case, let me say something simple like, so you have XB. I'm going to say that my coupling transform does something like XB minus theta, something like that, right? So this is a very simple transformation which is easy to invert. You'll see how it becomes invertible. So if I want to invert this entire function, I'm going in the reverse direction, right? So given Z, how do I get back to my X? Well, if I just split Z into two halves, I get the first half of my X, right? And since the first half was the same in the forward transformation and the reverse transformation, I can pass it through the coupling network to get the same set of parameters theta. And since I assume that the transform that you're applying on the second half is something simple, like in the earlier case, I just did a subtraction. So to get the inverse, what you would do? You would do addition, right? So here it would be ZB plus theta, right? Make sense? So what you get is you get the input back from the transformation, the original X back from your Z, right? So this is a very simple but cool way of transforming a transformation that is invertible. And if you look at this network is a neural model, which means the output that you get is not really an affine transformation. It's a nonlinear transformation for the second half. But you would be wondering your first half is the same, right? How does it work if I'm just gonna keep on applying these transformations? Half of my space would remain the same. But I'll get to that, what do you do. But let's also see how the Jacobian of this transformation looks like, right? So what you really have is you have two halves. I'm going to divide the entire set of features into two halves. I'm going to call it XA, XB, and the corresponding transformations as ZA, ZB. Now, if I compute the Jacobian for this transformation, I am basically differentiating each of this output with respect to the input. So I'll have a component that differentiates ZA with respect to XA, a component that differentiates ZA with respect to XB, that differentiates ZB with respect to XA, and ZB with respect to XB. Right? Now, how does this look like? Well, ZA, I know that it is directly like the same as my XA. So if I differentiate it with respect to XA, I'll get 1, right? It's identity. I also know that ZA was not transformed in any way. It does not influence on any. It has no influence from the XB side, which means if I differentiate ZA with respect to XB, it is 0, right? Now, if I try to differentiate ZB with respect to XA, then I have a very complex term that because I have a neural model here and I'm going to backpropagate all the gradients through the neural model. So I have some huge complex term when I differentiate ZB with respect to XA. Let's just leave that there. I'm just going to say it's a complex term. And if you look at ZB with respect to XB, you had some simple transformation, right? So if I had something like Z or like x minus theta and you differentiate with respect to x, you're going to get 1. If you have some other simple transformation, you'll get some other simple Jacobian in that case. Now, the good thing is, okay, you might be wondering this is also hard to compute because you have a huge term that involves a neural model here. But the good thing is when you compute a Jacobian, the determinant of the Jacobian, this term would go to 0 because you would be multiplying it with 0. All you would need is the diagonal entries, right? Which means you can compute this Jacobian very efficiently in order of D. This is a block diagonal Jacobian. So the determinant computation is efficient and you can do it in order of D linear time instead of cubic time. Right. So coming back to the question, okay, wait. So let me ask if you have any questions here on this slide, how this becomes invertible. Right, the coupling network is the same. And since the input remains the same in forward and reverse, you'll get the same output from your coupling network, right? It doesn't have to be equal. You can have arbitrarily splitting. What's important is that you split it the same way when you're coming in the reverse direction, right? Yeah, that is one of the ways in which you make it efficient. Right? You don't always need it to be diagonal, right? But I'm making the point that if it is diagonal, then computing that determinant takes only linear time, right? And it makes things efficient. Any questions here? So the motivation is to come up with it's more derived from like how can you come up with an invertible transformation that also has an efficient Jacobian determinant, right? That is the motivation, because it's not easy to invert a neural transformation. You need to define this transformation in some way or have additional properties defined so that they become invertible, right? And this idea of having a coupling network is like one of the ideas. Yeah.
What I meant to ask was this kind of splitting and passing it through a coupling network. Why does it? What's the intuition for doing it that way?
I mean, it makes things invertible. I do not know how they came up with it, right? What motivated them to think of a coupling network, but maybe they constructed it backwards, or like, yeah. But it works. Like it's something cool. I don't have an answer for like how they came up with it, right? But makes sense, right? The idea makes sense, right? All right. Yeah, please.
What about the dimensionality?
Yes, good question, right? So for normalizing flows, that is one of the issues, right? Because if you think of models like VAEs, you are assuming that your factors of variation or the latent space lies in a lower dimensional space than your data. You can have a more compact representation than your data space itself. But when it comes to normalizing flows, to ensure that your model is invertible, you need to ensure that the data dimension is the same before and after the transformation, right? So each of these transformations themselves would also maintain the data dimensions. You cannot reduce the dimension because it would result in loss of information. But there are recent works that like tries to do injective transformations and have an approximation for the inverse of it. Yep.
This should be a big limitation, right?
It is in terms of computations, right? In terms of how much it is computationally inefficient, because your latent space is not, if you were to follow the manifold hypothesis, what it says is that your data is really dying on a low dimensional manifold, right? And you are sort of putting an importance over the entire space, which means you are, you have a lot of wastage in terms of your parameters, right? So it is computationally more expensive, but then you also get tractability along with it, right? That's the point. Yeah.
So we are having this issue of not able to reduce the dimensionality.
Mm-hmm.
So will that also mean like we will fit to the noises in our data? Because that's one thing which we get heavily
Fit to the noise in your data.
So as your explanation,
Mm-hmm.
the data lies in a small manifold.
Right.
But
Right.
here we are not getting that.
Yeah, so there are like limitations with flows, especially when you have data distributions that lie explicitly on a manifold, right? This was one of the things that I like, one of the research problems that I worked on. So when you have these transformations, invertible differentiable transformations, which are called diffeomorphisms, they cannot map between two spaces which are topologically different, right? So you're assuming that the topology is the same in both spaces. So if you have things like holes in your distributions, etc., in one space, you cannot have that in the other space. So if you have disconnected components in one space and you have a single component in the other space, then those spaces are, they can be like topologically different. And a flow, by definition, an invertible, or just from a mathematical sense, any diffeomorphism cannot map between such topologically different spaces, right? So you need to find some additional extensions, improvements to these flow architectures to counter for that. And one of the ways we did it was to define mixtures, right? So you restrict a flow in terms of its support, right? So when you have a huge manifold, you sort of decompose the manifold into smaller regions, which look locally like a Euclidean space instead of manifolds, and then you fit a flow over those small regions and you combine them with a mixture. That's like, so yeah, so all those aspects do remain, right? There are issues even with these classes of models that needs to be addressed. Yeah. Okay, any more questions? Okay, so one of the confusions here was that if you just simply compose these coupling transformations, your entire one half of your data space would remain unchanged, right? Because you are simply copying the first half into the output of your like transformation. So how do you deal with that? Well, I can still compose these coupling transformations. All I have to add is a permutation layer in between these transformations. Now, a permutation, you can mathematically represent it as multiplication with a 0-1 matrix, right? And it is an invertible operation because think of this matrix here. So I have a matrix A, and if I want to permute this matrix such that this row comes to the top, then all I'm really doing is I'm multiplying it with a matrix, a 0-1 matrix, which has exactly one element that is 1 in each row and each column, right? And such a matrix is invertible because the inverse of a permutation matrix is the transpose of the permutation matrix, right? So I can permute any given matrix by multiplying it with a permutation matrix. I can get the same inverse of that transformation by multiplying it again with the transpose of the permutation matrix. Now what you have is, okay, a good way to compose these coupling transformations and ensure that the entire space is still transformed. What you do is, okay, you start with XA, you copy it into YA, you have XB, you transform it using XA into YB, but now I permute XA and I permute the elements in this vector, right, using a permutation layer, and this permutation layer is invertible, and since this is a 0-1 matrix, the Jacobian of this particular matrix has determinant 1, which means it does not alter the volume of the space in any way, right? So you don't have to worry about Jacobian computations as well here, and the entire thing is invertible as well. Good. Okay, so I told you about the coupling network and that you have some simple transformations that you use from the by getting parameters from your coupling network. But what do these transformations actually look like? Now, people have explored different types of simple transformations. The most simplest thing I can think of was what I mentioned, right, where you just do an addition. You add the second half with whatever you're getting from your neural model. That is invertible because all you have to do is do a subtraction. You can also take an affine transformation, which is more common, This was proposed in 2017, and it was called real NVP, or real non-volume preserving flow. What you do is, okay, you take the second half, you multiply it with some factor, so you scale it and then you translate it, right? And all you have to ensure is that the factor that you are scaling it with is not 0, right? As long as you ensure that this is not 0, then you can invert it, because all you have to do is take the reciprocal and multiply it, right? So there are more complex things people have looked at, like even some formulations of MLPs and splines, etc. But I hope you get the gist of it as to how you define one such invertible transformation that has an easily computable Jacobian determinant, right? Should we take a 2-minute break? Okay. 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 Now, okay, one of the good things you can do when you have such a model is that, so you know that in the data space you have some complex manifold that you do not know, right? But in the latent space, things are very simple. Now, I can use this knowledge to do things like interpolation very easily. Let's say, like I have a data point that looks like Professor Sriraam, and a data point that looks like Professor Ravindran that lies somewhere on this complex manifold, right? If I were to directly take an interpolation in the data space, I would most likely come up with something that looks like noise, because when you interpolate, you don't know the manifold. It's very likely that your interpolated point lies outside of your manifold, right? But in the Gaussian space, things are much more simple. It looks like it's a Euclidean space, and when you interpolate in this space, what you get is a data point that lies on the manifold itself, right? So you can do very cool things. People have done interpolated. So the first picture is the author of the real NVP paper, and he has shown how he has interpolated between different famous people, right? So those are interesting things you can do. What you can also do is identify certain directions in your latent features that have semantic meaning. So one of the very hot topics even in representation learning and VAEs is how do you learn representations that are disentangled, right? How do you learn disentangled representations where you have some sort of semantics associated with different dimensions of your latent feature, right? Now, such a thing can be achieved in a normalizing flow. To some extent, it's approximate, right? But always it's approximate, but it's easy to do that. So how do you do it? Let's say that I wanna look at directions. I want to look at features or things that change. So if I have a model that has approximated faces of people, and I know that people can be happy or sad, right? Now, which direction in my space do I have to go to make a person from happy to sad? What I can do is I can look at where the distribution, where the images of happy people lie, right? And I can also take an image in which the person is sad. I can look at this Z space, the latent space, which is simple, and if I interpolate in this Z space, I can get a continuous transformation from between these two emotions, right? So things like that. So you can come up with semantic associations for the different directions that you have in this latent space, right? So there are cool things that you can do. I also have a demo on normalizing flows. We'll actually implement the coupling transform and the interpolation that we saw from scratch. Can we do that? I think, yeah, we can do. I can walk you through it. Did you guys receive an email with the GitHub repository with the code and stuff? Okay, so all these notebooks are uploaded on the repository. You can play around with it, right? So this is a collab notebook in which we'll implement the coupling transform that we just discussed, right? How does it look like? Well, just as we said, we are interested in transforming the first half, like splitting the data into two, keeping the first half the same, transforming the second half conditioned on the first half, right? We'll be using PyTorch to implement this model. But first, let's create a simple synthetic 2D data set. This is a data set. Let me see if I have a visualization. So this looks like something like a spiral. It's in a 2D space, but it lies on a lower dimensional manifold, right? It's in 2D space, but it's a manifold data distribution. Okay, now how do I define a normalizing flow? What all things do you have to specify in a normalizing flow? If you're defining a model, if you're defining a neural model, all you typically do is define the forward transformation, right? When you give in x, how does it transform the data f of x? But when you define a flow, you have to define both f of x and also the inverse, f inverse of x. You'll also have to define the Jacobian determinant so that you can do density evaluation exactly, right? So in this case, I'm going to define a list of coupling transformations. I'm just going to put it in a torch module list. I'm going to specify what my base distribution looks like. So in this case, I have a normal distribution. You can also have learnable parameters for these normal distributions or more complex distributions than a normal. You can have mixtures of normal distributions and things like that. But here I'm just keeping it very simple, right? Okay, so now you have a function that computes the probability density. What the probability density looks like is when you make a forward pass through a flow transformation, I'm saying that it outputs the, so if I'm starting from the Z space, what I'm doing is I'm computing the probability density in the Z space, and then I have the Jacobian determinant, which is the volume correction term, right? But like we said yesterday, even for probabilistic circuits, we typically like to work in the log space than in the actual probability space, because you can easily get an underflow in the original space, right? So when you do computations in the log space, what it reduces to is, if you have a product and you take a log of the product, you're basically adding the two logs, right? So you have a log likelihood coming in from your flow transformation, and then you have the log of your determinant Jacobian, and when you add both, you get the log density, right, using the change of variables formula. Now, how do you do sampling? It's moving in the reverse direction, right? I sample from a simple normal distribution, and I apply the inverse of my bijections Z. Good. Okay, so I haven't yet defined what these bijections are, or these transformations themselves. So instead of doing a permutation, what I'll do is I'll just flip my entire tensor along the dimension, right? Because if I am transforming the first half and I want to transform the second half, I can still use a transformation that works on one region. All I have to do is invert the input, right? So I can just flip the input along the dimension, and then that will ensure that when I compose these transformations, you cover the entire space. So instead of a permutation layer, I'm just going to use a flip layer. It's easy to do the inverse. All I have to do is, again, flip it one more time, right? Now I can go ahead and define the coupling transformation, the coupling layer that we discussed. What it does is it splits your input x into two. You can split it arbitrarily as well. So here I'm just splitting it into like two without any sort of random order. Now I pass the first half through a neural model. You can have any neural model that you want. You can have a feed-forward layer, convolution layer. It depends on what data that you have, right? Okay. So what I do is I pass the first half through a neural model, and I compute two parameters, which is the scale and transform parameters. Now I'm going to scale the second half of my input with the scale parameter, and then I'm going to translate it. So that defines the transformation for my second half. I'm going to define the final output as just the concatenation of my first half and the transformed second half. Make sense? I also have the determinant Jacobian to compute, right? But in this case, when I compute the determinant Jacobian, it's just summing over the scale transformations. So if you remember, what we had when we looked at the Jacobian, we had an identity in the first part, right? 0 in the second part, and then you had the Jacobian of the transformation you're defining in the lower half, right? So when you compute the determinant Jacobian, the Jacobian determinant, it's basically the Jacobian of your simple transformation, right? So you're only transforming the second half, and if you compute the derivative of x2 with respect, or z2 with respect to x2, what you would get is s, right? If I am computing the partial derivative of z2 with respect to x2, all you will get is s, right? Because my z2 is s times x plus t. Makes sense? I don't know if I can write it here. Okay, so in the same way, I can define the inverse transformation. It's just coding of the exact thing that we discussed, right? I have my latent feature. I split it into two. In the same way, I splitted my data x. Now I pass the first half through the same neural model. Now since the first half was unchanged, I will get the same scale and translate parameters. Now what I do is I apply the inverse of my simple affine transformation, where I remove the translation and I scale it by taking the reciprocal. So here I'm working in the log space, which is why I have to take an exponent, right? But the idea is the same, right? All right. So you can have arbitrarily complex neural models that do your coupling transformation. Here it's just a feed-forward layer, and you can create a normalizing flow by stacking these coupling and permutation layers to an arbitrary depth, right? So the more transformations you have, you'll have more parameters, and you can learn more complex models. Right? So in this notebook, you can set the different hyperparameters. You can set the learning rate. You're just going to use maximum likelihood and gradient descent to train the flow. But you can play around with all these hyperparameters like learning rate, batch size, how many hidden dimensions you need in your neural network, how many flow transformations are you going to use. You can play around with this and see how it affects how fast your model learns or how slow it learns, if there are any instabilities in the training of the model. All those things you can like play around with. But it's just like training a neural model. What I'm going to do is define the model, create an optimizer over the parameters of the model, provide a learning rate. This is what the model looks like. And then I'm just going to make a forward pass, sample data from my data set, make a forward pass to my normalizing flow to get the log likelihood. I backpropagate the log likelihood to the parameters, and then I take a step using my optimizer, right? And this is visually what it looks like when you initially start. You have the generated data on the right that looks like noise, but as you keep on training, it slowly learns the distribution. Not perfectly, because I haven't played around with this a lot, but you can play around with it and make it better. Okay, we can also visualize how the distribution is being transformed by each individual layer in this flow. So as I'm passing it through, so I have 1, 2, 3, 4, 5, 6, 7, 8, 9. I guess I have 10 layers here. And if I visualize what the data looks like after each step of transformation, this is what it looks like. Right? It's doing some sort of folding, warping in the space until it looks something like a simple Gaussian. Right? Okay, so that was a simple 2D data set. People have also done this for like very complex image data sets. What we will do is we'll just import a pre-trained model. This is a different version of an invertible transformation, which are called residual flows. If you're interested, please look at this paper. But the idea is the same. It's almost the same. It's more like how you come up with a neural transformation that is invertible and has efficient Jacobian determinant. And what I'm going to do is I'm just going to load the pre-trained weights and show you how you can utilize these models to do some of the interpolation and stuff that we saw on the slides, right? So in this case, I've loaded a model that was trained on the celeb A face dataset. Here are some samples generated from this model. It's not very realistic, but still it's okay. Now what I can do is I can do this latent space interpolation by giving it to a source and a target image, right? So I'm loading 2 images here, one of Professor Sriraam and one of Professor Ravindran. Now what I can do is I can come up with what is the latent feature corresponding to each of these inputs. Now for each of these inputs, for every input, for every data point x, since you have an invertible function, you will have a unique latent feature, unique z associated with it, right? So I can compute what the z for my source image is. I can compute what the z for my target image is just by doing a forward pass using my model. And I can interpolate. You can do any sort of interpolation. I'm just doing a linear interpolation here. You can easily interpolate in this z space and see what variations happen along the direction you're interpolating in the data space, right? So in this case, you'll see that you'll have a more continuous transformation between the 2 data points itself, right? So this is what it looks like. Yeah, that's pretty much it. You can play around with this, see how the flow eventually transforms your data distribution. But this is like a very, very cool line of research I enjoy. I used to like think about how you can build these neural transformations more effectively, but I also got interested in making them more tractable, right? And that is what we will come into like talk about in the next part of this session. Right. So far what we just did was we took a sort of a detour and discussed a deep generative model called normalizing flows. Right. Now what I will say, what I will get to in the next part is how you can combine both, how you can combine the inductive biases in normalizing flows with the things that we already know in a probabilistic circuit to build a hybrid class of models, which are also tractable for things like marginals and conditionals, but you also gain some of the expressivity from a normalizing flow. Yeah, makes sense? Any questions? Yeah.
So, just interested by this interpolation example.
Mm-hmm.
So, we do this in variation order encoder. In
Mm-hmm.
order to get this smooth distribution, we add, the latent variable is sampled from a standard normal distribution, and we add a error so
Mm-hmm.
that
Yeah.
the distribution becomes smoother. So, how are we
Right.
achieving smoothness in this?
So there, it's more like an optimization problem, right? You have to find, you'll have to ensure that smoothness in a VAE, right? Here, it is ensured by the invertibility structure of your transformation itself. So one of the issues with training VAEs is that you can have something like posterior collapse, where your latent information, they are not really informative of the data itself. So z given x can just collapse to p of z, in which case you do not have any way of, you do not have a unique, you anyway do not have a unique a unique latent feature for each x. But here, since you have the invertibility structure, given any x, you will always be able to find what the exact unique latent representation for it would be, right? And that representation lies, we assumed it to lie in a Gaussian space, and we trained to ensure that it lies in a Gaussian space. So interpolating in this space makes it smooth because of the properties of your Gaussian. It's a Euclidean space. You have the support of the distribution over the entire space, right? So when you interpolate in this space, you're going to get a smooth interpolation in your data space. That makes sense?
This we can't guarantee in the intermediate layers, right? So we can guarantee this in the
Right.
final layer where we have assumed it to be Gaussian, but we can't guarantee this in the
Right, right. So in the intermediate layer, you cannot guarantee that you will have such a smooth transformation. Yep. That's a good point. Any more questions? I think we can take a break before we move into the next part. Yeah, 40, 50, 45.
So we'll be back around 10:45. So I apologize, I have to take off because I have a meeting at 11. But I trust Sahil will finish up the rest of it. So sorry, I couldn't make it. So you take care of this. I'll see you on. Perfect.
All right. Shall we get started? Everyone back? Okay. Hope you had a short but good break from all the technical details. But let's see if we can get back to some of it. So the discussion, if you remember, we were talking of normalizing flows, right? And the context in which we were discussing normalizing flows is that they are deep generative models which are expressive and can do a lot of cool stuff, but they are not still as tractable as your probabilistic circuits. And we are interested in building models that can sort of interpolate on the spectrum of tractability and expressivity, right? Because in many tasks, you really don't need tractability of inference for everything, right? It really depends on the task you have. You might only need tractability for a certain subsets of variables or things like that. But when you have such a domain, how do you have a model that can interpolate on the spectrum and have the tractability that you need, but also has the expressivity enough to model, the complex distribution? So what we'll do is, okay, so as an expressive model, we'll take normalizing flows as an example, and as tractable model, we have our PCs, and we ask the question how you can combine both of these model classes to build a hybrid model that achieves the best of both, right? So if I were to go back to the normalizing flow and think what a flow does, all it does is it takes a simple distribution and it transforms the simple distributions through a sequence of invertible steps to get something more complex, right? So you have a base distribution and you're applying the change of variables formula by parameterizing an invertible function using a neural network, right? And applying the change of variables formula to get a more complex probability density or probability mass, right? Like, and if I think of what a probabilistic circuit does, it is also transforming distributions. It is starting with some simple leaf distributions, and it is transforming it into something more complex by products and sums, right? So one intuitive way to like combine the change of variables formula or the normalizing flows with probabilistic circuits would be to extend the representation of a probabilistic circuit itself and introduce a new type of node in this graph, which does this change of variables formula or the neural transformation, right? So let's see how that can be done. Let me just call the such normalizing flow nodes as transform nodes. All it does is it applies the change of variables formula, or let me see. Okay, so if I have a PC, each internal node in my PC is computing some probability distribution, right? Now I can think of that distribution as the base distribution for a flow and transform it into something more complex by having an invertible transformation on top of it. Okay? So what I do is, okay, let's see, for example, I have a product node. I can add a transform node over it and treat the density or the the distribution that I have at the product node as my base distribution, and then have an invertible transformation here that transforms that density into something more complex. I can also do the same thing over a sum node, right? So one way to extend and build a hybrid class of models would be to add an additional node in your PC that does this change of variables formula through an invertible neural transformation, right? So such a model would definitely add expressivity to your probabilistic circuit, right? But the question then you have is, okay, if you add these wait, before I get there, so here's the high level view. So if I have a transform node introduced into a probabilistic circuit and it can be defined arbitrarily over any nodes in my circuit, then one way to combine both would be to place the transform nodes arbitrarily over my probabilistic circuit, right? But obviously the question is, well, if I can do that, then I mean, and I'm not defining anything, any other structural restrictions on this, then isn't it as good as a normalizing flow? Because I'm adding normalizing flow nodes in between a PC. How can I get the same tractability of a PC and the expressivity of a normalizing flow without losing anything? It just doesn't make sense, right? There's no free lunch. So what we did, so we tried to study this problem. So there was a paper in PGM that proposed this hybrid model in which you arbitrarily place transform nodes in a circuit, right? But when we studied this, we realized that, okay, when you build such a hybrid model, it is not really tractable for the things that a PC is tractable for. It can still only do evidential inference. You cannot do marginals and conditionals over such a hybrid model, right? So we had a paper in WSAI 2023 where we proved that when you have such a construction, you can never construct a PC that is always decomposable, right? So such a construction will always violate the decomposability property of a PC, which means you cannot push down the integrals that are involved in your marginals and conditionals. So the way we like proved that PCs can do tractable marginal and conditional inference was that we started with the integral or summations involved in these computations, and we showed that they can be pushed from a root node until you reach the leaf nodes, right? But when you have these transform nodes in between, what happens is that these integrals can no longer be pushed down. They block the pushing down, right? So as a result, marginal and conditional inference becomes intractable. And the way we made things tractable for a probabilistic circuit was by defining structural properties, right? So we defined smoothness, we defined decomposability, and showed that you have marginal and conditional inference to be tractable. And then to get something like map, we had to define more structural properties. We had to define the determinism property, right? So it is expected that when you introduce a new type of node, transform node, into your probabilistic circuit, and you want to still retain the tractability, you'll also have to define properties over this node. When those properties are satisfied, that you can do the inference task in an exact and efficient way, right? So what are those structural properties? We call it tau decomposability just because it's decomposability defined over your transform nodes. So if you remember what a normalizing flow transformation did, it transformed your data into a feature by applying an invertible transformation, but there was no restriction on how this transformation linked the different parts in your data, right? So initially it could have been, so when you did a normalizing flow, you computed say x1 and x2 or z1 and z2 from x1 and x2. The way we defined a coupling transform, z1 we had copied x1 to z1 and x2 was transformed by conditioned on x1 to get z2, right? But when you do this a sufficient number of times, right, all the features in your latent space becomes dependent with all the features in your data space, right? There is no sort of decomposition, right? So if you have a transformation that correlates each dimension in your latent space with each dimension in your data space, such a transformation is not tau decomposable, and we sort of showed that. So there's a whole proof and mathematical definitions for this. I won't get into that, but the idea is that when you have an normalizing flow transformation that makes things dependent, that makes different random variables dependent, then if you have a product node in your circuit, the transform nodes would cause the children of product nodes to be dependent as well, which means you will not be able to satisfy the decomposability property. Now, to satisfy the decomposability property, what you can instead do is make sure that if I have a transform node defined over a product node, let's say this is a product node, this is a transform node, and I have a product node to be over x1, x2 here, and x3, x4 here, right? Now, if I have a transform node, now the transform node works on the entire space of x1, x2, x3, and x4, right? And I'm transforming this into z1, z2, z3, and z4. Now, if I were to define a property for this transform node that doesn't satisfy the decomposability of a product node, then I can say that you can push the integrals down from the transform node. Now, what is the property that it needs to satisfy? Well, here in the product node, I'm saying that x1 and x2 are independent from x3 and x4, right? So I have to define a transformation that respects this independence. How can I do that? So when I compute z1 and z2, it should depend only on x1 and x2, and z3 and z4 should depend only on x3 and x4. If you have such a transformation, then you call it as tau decomposable. And what you can show that is such a structure, such a property of tau decomposability is in fact a necessary condition for tractability when you are building these hybrid models where you're combining normalizing flows with probabilistic circuits. Now, to give you an idea of why things become tractable, so if you're computing an integral over a transform node defined over a product node, which is what you would do if you're doing marginal or conditional inference, you can sort of show that this is equivalent. Oops, did I mess something up? Yeah, so computing this integral, you can prove that this is equivalent to pushing the integral together with the transformation itself to the child of a product node, right? So this is just to link with the idea of how we made things tractable, right? It was by pushing complex things from the root node to the child node where it can be easily computed. And we are asking, if you have a transform node, can you still push things down and make things tractable, right? So it turns out that if your transform node satisfies this property of tau decomposability, then you can not just push the integral, but you have to push the integral together with the transform node itself from a node to its children. But what happens is, okay, if you have a probabilistic circuit in which you also have transformation nodes introduced or normalizing flow introduced in between, and you ensure that these transformations are tau decomposable, then you will end up pushing each of these transformations from a node to its children until you reach the leaves. Now, what this boils down to is that you have a hybrid model in which you have a probabilistic circuit, but at the leaf level, instead of having simple tractable distributions, you have something more complex. You have a normalizing flow defined at the leaves, right? So we call this class of models as probabilistic flow circuits. And in fact, if you really want to retain both expressivity and tractability, this is the only thing you can do, because having tau decomposability is a necessary condition for maintaining tractability, right? So how does this look like? So let's say this is my initial PC, which is computing a mixture over 4 components. Now, if I were to have a probabilistic flow circuit, instead of having simple leaf distributions, I will be transforming the simple leaf distributions with a normalizing flow to get something more complex. right? So having a normalizing flow at the leaves increases the expressivity of your model because you can model arbitrarily complex distributions at the leaves, and it also retains the tractability that you had for like conditionals and marginals in a PC, right? So here's a real life example of how it improves your expressivity. Let's say that you're interested in modeling this circular data distribution, and you have a PC that looks like this, right, which is a simple mixture of 4 components. Now, if you use this PC, all you can do is model something like a square. You cannot model the circular distribution very accurately because you have simple leaf distributions. But if you have a normalizing flow defined over the leaves with the same PC structure, this is important, right? It has the same structure as your PC. It's just that your leaves are now normalizing flows. You can better approximate the circular distribution because at the leaves you can now learn distributions that are multimodal. So initially, when you had things like a Gaussian distribution at the leaves, you had a limit in your expressivity. But now by having a flow, you can have arbitrarily complex leaf distributions, which means you can model more complex distributions, joint distributions easily. That makes sense? Any questions? Yeah?
Transformations that are used at different places, they have different parameterizations, right?
Right. So that's the point, right? So if you really want to ensure tau decomposability, what you will have to, so if it's defined over a product node, you'll have to make the transformation in such a way that it maintains, it respects that independencies in your product node, right? So we are not constructing this by introducing it in between. What we are saying is we are taking a theoretical view, right? Okay, we are constructing a theoretical model in which we are introducing transform nodes arbitrarily in the circuit, right? And what we are saying is, okay, if you really want to retain tractability in such a model, you have certain properties to be enforced, which is tau decomposability. And then what we show is that if tau decomposability is in fact enforced in this theoretical model, this model is equivalent to having the transformations defined just over the leaves. So instead of defining this arbitrarily, when you implement it, you just define it over the univariate leaf distributions. Make sense? Okay. Yeah.
When you use tau decomposability,
Mhm.
you're enforcing it. How does it learn the function of transformation?
So this is everything from a theoretical standpoint, right? We are not enforcing tau decomposability because we are not putting the transform nodes arbitrarily in the circuit. So this is a theoretical line of argument that if you were to come up with a hybrid model in which you place transform nodes arbitrarily, such a model will not be tractable. You will need tau decomposability, right? And when you enforce that, then it boils down to having the flows defined just over the leaves. So when you actually build the model and train the model, you are just having flows at the leaves, right? So you don't have transform nodes in between. You don't need tau to enforce tau decomposability, right? Makes sense? Any more questions? Okay. All right. So we have a questions? No. Okay. So we also experimentally validated that the resulting model has added expressivity and also better learning efficiency over a PC. So it learns much more faster than a PC learns. So we had a lot of manifold data distributions over like 3-dimensional spaces. And what we observed was that having a normalizing flow at the leaves not only resulted in the model getting a better likelihood value or better performance, better fitting the distribution, but it also typically did it much more faster, right? It achieved a higher likelihood score much faster than the basic PC itself. We also benchmarked this on several tabular density estimation data sets, right? And we saw that you receive you achieve performance that is at par with many deep generative models. So MAIR, real MVP, and masked autoregressive flows, MAF, these are all normalizing flows themselves, right? And on density estimation tasks on tabular data, you are able to achieve or even outperform some of the normalizing flow models by having a PC with normalizing flow at the leaves, right? So it's able to achieve competitive performance, right, as a deep generative model, but it has the added tractability. Now, we also experimentally validated that the model is tractable for conditionals and marginals. So you have the same task that we saw yesterday, in which we were making occlusions. We are cutting out half of the image, and we were generating from the conditional distribution over the occluded image. and you see that things look plausible, right? What you can also do with the tractable model is now you can have some more control over the data generating process itself. So, for example, if you have a data distribution that looks like this spiral, and you're not really interested in data from the entire space, but what you really want to do is generate data, the 2D projection of which looks like this particular arc. You can specify that as the conditioning and generate from the conditional distribution. So you can generate from different parts of your data distribution that you're interested in by performing conditioning and things like that. Right? So this is still a toy example, right? Not real life. Sorry about that, but just to make the point that what capabilities do these models have. Yep. All right. So let me just walk you through a notebook that does this. So in this, this is the last demo that we have as part of this workshop, right? So what we will do is we'll just see how a classical probabilistic circuit or a deprobabilistic circuit compares with a hybrid model, right? A probabilistic flow circuit in which you have a normalizing flow defined over the leaves. I'm not gonna define everything from scratch. I'm basically just gonna import. There's a GitHub repository that's publicly available for probabilistic flow circuits. Feel free to play around with it and see if you can use it for your applications. But in the same way that we learned a deep PC yesterday, right, we can train the model in the same way. So I'm creating a synthetic spiral data set here. And I have an ensemble network which we discussed today that tries to learn this data distribution, but this distribution has some structure. It lies on a manifold, right? So what you will see is this model has trouble learning this data set even at the end of 200 epochs. So this is something that it learns at the end of 200 epochs. Now what if we were to define a normalizing flow at the leaves, but with the same set of parameters for your PC, it's just the leaf that is changing. So if you look above, you have the same set of parameters, but in this case you have a normalizing flow defined over the leaves, right? So what you see is that this model learns the data distribution much faster and much better than just having Gaussian distributions at your leaf in a PC, right? This is again at the end of 200 epochs. Right, so you can, I'm not going to go in depth because the training procedure, everything is the same. And what you can do now with this class of models is, this is valid for probabilistic circuits as well, or tractable models, is you can do control generation where you can generate samples from regions in your support that you're really interested in or you have some idea about, right? Now it would be interesting to see if you can also incorporate some sort of domain knowledge, right? And understand which parts in your so in generative models you could overfit, right? Because at the end of the day it's a mixture model. So if you have an over parameterized model and you have a few amounts of data and you're training it for a large number of epochs, then it could just overfit to your training examples itself, right? But an easy way to check that is to generate samples from it or evaluate it on a test set. So if you look at it's the same way how you would train a neural model, right? You'll have a separate validation set on which you evaluate the model's performance. So here you compute the validation log likelihood, which is on a separate set, and you see that even when your train likelihood decreases, your validation likelihood also, or train likelihood increases, your validation likelihood also increases, right? So you ensure that your model is not overfitting. But there is always a chance for overfitting, like you said, and there are a lot of works that tries to come up with regularizations and architectures that avoid, that can counter overfitting. Yep. Okay, so the point is having a more expressive flow transformations at the leaves of a PC helps. So in many datasets, you do not know what the manifold is or what architecture do you need, how much parameterization or over parameterization do you need in a PC, right? So in such cases, having a flow gives you that flexibility that even if your data is more complex, your flows can take care of it, right, at the leaves. So that's the whole point, but feel free to like play around with this. I won't spend more time here. Okay, so we have, let's try to wrap it in another 30 minutes. So what I will do is I'll skip a couple of slides and I will move to applications, right? Let me see, how do I present? Okay, so I hope you now have like a broad idea of the like research directions that we work on, and also a rough idea of what tractable models look like and where the research is progressing in terms of bridging the gap between these tractable probabilistic models and deep generative models, right? It's more like coming up with more inductive biases borrowed from the deep learning side of things, incorporating it into the classical tractable models to bridge to make things both expressive and tractable. Now, a question that many of you like have and have asked me also is like, where are these models actually applicable? Now, applications is something that is also being like actively worked on, because this field has got a lot of interest, especially the deep part of it has got a lot of interest in recent like 5 years, right? So people are using it for different applications, but I thought I'll discuss two interesting applications that I find most exciting. The first one is constraint generation, but not constraint generation from a PC itself. What I'm interested in doing is I'm taking a deep generative model, something like an autoregressive language model, and I'm asking the question, can I enforce it to generate samples that satisfy certain constraints? Well, you would be thinking that, okay, why can't I just mention the constraints that I have to the model itself and it will take care of it, right? So if I want ChatGPT to generate something that has that has to contain some information that I want, I can just specify it to it, right? So for example, if I want to create a sentence that contains the word research talk, Sriraam, and IIT Madras, and I want the sentence to contain all those words in the same order, I can tell ChatGPT to just generate it in the same order, right? But what happens is it does not really have the capability to ensure that those constraints are always satisfied. So in this case, if I ask it to generate a sentence with Sriraam research talk or research talk Sriraam and IIT Madras in the given order, it clearly messes up the order. It generates a sentence which is factually correct, which looks which is a high quality sentence, but it cannot satisfy the constraint that it does not satisfy the constraint that I gave it, right? So how do you do constraint generation? Now, the key idea that you will see in this particular, so there are other works as well that looks at it, but the key idea is here is that you take a deep model that does not have the ability to do constraint generation, but you take a tractable probabilistic model over which you can do constraint generation by having conditionals, right? And then you come up with a way to combine both, so or sort of guide the generative process in your deep models, right? That is like one application. And what I will discuss here is on the language side, generative models for language, but people have also done it for image models in diffusion models, right? How you can do the same thing for diffusion models. Okay, so what does text generation look like? Let me give you a brief intro of, so is everyone, okay, let me ask this. We have all used ChatGPT and language models, but do you have an idea of how language models work, like from a generative standpoint? Yep, okay, good. So it's basically the chain rule of probability, right? Any probability distribution, you can write it down. Let's say I'm interested in a distribution over x1, xn. You can think of each xi as a word or as a token, right? And if I have a text, if I have a sentence, it's basically a collection of such random variables. And how do I come up with the probability of, how do I decompose the probability, the joint distribution? I can use the chain rule. What does the chain rule say? I can write it down as p of x1 times p of x2 given x1 times p of x3 given x1 comma x2, etc. until p of xn given x1 to n minus 1, right? This is basically the chain rule of probability, but if you write it down this way, you call this an autoregressive formulation, right? So you generate one token at a time, conditioning on whatever you have generated so far, right? So for example, if you have generated so far the prefix that the weather in Madras is, how would you generate the next token? So everything up till this is something you have already generated. You're interested in generating the token at x time t, xt, right? and you want to keep on continuing this. But the way you generate this entire sentence is one token at a time. Right? So you look at the distribution over capital XT, which is a variable over all your vocabulary, given that your prefix is the weather is Madras. So this will give you a distribution over your entire vocabulary as to how likely each word is as the next token. And then you choose, you can have different sampling strategies, but here I'm just choosing the word that is most likely. Right? So this is typically how text generation works in sequential models, even in transformers. Now, if I were to extend this to constrained text generation, what I'm asking is, okay, I have the prefix that the weather in Madras is. I want to complete that sentence, but I also have the constraint that it should contain the word summer. Right? When you complete this sentence, there should be summer somewhere in this sentence. Now, this is a bit hard because what you're really doing is, okay, now I'm not just interested in picking the word that maximizes my conditional distribution over the next token given everything else, but I'm interested in looking at the next token such that this condition is satisfied. So if I were to keep on generating like the next sequence of tokens, the word summer would appear somewhere eventually, right? So you have to look ahead into the future to see if generating this particular token here would affect the likelihood of generating the word summer sometime into the future, right? So this is not very easy to solve, even like in the classical formulation. Or another way to do this or like formulate this is you look at the distribution over the next word given the prefix word, given the prefix that you have already generated, but also the constraint that you have, right, must contain the word summer. Okay, so if you were to incorporate this, if you were to come up with a model that can do constraint generation, ideally the likelihood of the next word that you are generating should be 0 if generating that particular token makes it impossible for you to satisfy the constraint, right? So you should never generate, so the crux is that you should never generate a next token that will make it hard or make it impossible in the future for the constraint to be satisfied. And this is a hard problem because you cannot really look into what happens in the future, right? But probabilistically, what this boils down to is, let's see. So I can apply base rule here. I'm looking at probability of next word given prefix comma my constraint alpha, right? If I apply base rule, this is proportional to probability of, I can write this as alpha given p comma, wait, let me see, let's write this down. How do I get an eraser? I can write this as probability of n comma alpha given p times probability of alpha given p, right? But when you're generating the next word, I can again decompose this, the numerator here, as probability of alpha given n comma p times probability of n given p, right? This is the same. This is just the decomposition of your joint from base rule, right? So what you really have is you can decompose this probability distribution that you have as product of two distributions, right? The second one is nothing but the distribution over your next word given the prefix, which is the same thing that you did generation earlier from, but in addition to it, you are multiplying it with another probability that looks at the likelihood of your constraint being true, given that you are generating that particular next word and you have generated something so far, right? But the issue is, if you really want, this is something easy to compute. This comes directly from your neural model, right? It gives you. But how do you compute this particular term here? I'm sorry, I'm making a mess. Well, it turns out that this is nothing but doing marginal inference. You're marginalizing out over the suffixes that you want to generate, right? And looking at if those suffixes result in satisfying the constraint. So you can sort of formulate or write down this likelihood in which you are looking at the probability of this likelihood being satisfied as doing marginal inference over the next set of sequences of words that you're going to generate, right? But your model, your deep generative model, like a large language model or transformers or whatever you use, it cannot do marginalization tractably, right? Well, so what can we do instead? We know that probabilistic circuits are good at doing marginalizations, conditional inference, everything. So we somehow want to incorporate a PC to model that constraint and then mix it with the deep model so that you generate good quality text which satisfies the constraint. Now the way to do that is, okay, I have my deep model. I generate samples from my deep model which is already pre-trained. Now I fit a PC over the data that I generate from my deep model. Let me call my deep model M and my PC Q. So my deep model learns some distribution PQ. I want to learn a probabilistic circuit PM that is an approximation to PQ. And if I can do that, I can replace this particular term here, which is the likelihood, using my deep model instead. Okay, there is some issue. This is overlapping. So what I do is I can replace this M with Q as an approximation, right? So if I can do that, then I can do marginal inference over Q over my PC to compute this likelihood very efficiently, right? So you use a PC to approximate the first term. Now here's how it looks like. This framework is called Gelato, Generating Language with Tractable Constraints. This is proposed like last year's ICML, so it's very recent. So let's say I'm interested in computing a sentence that contains the keyword winter. Right? That is the constraint that I have, and my prefix so far is the weather is. So I have generated the 3 words the weather is, and I'm interested in looking at the next token that I would like to generate, right? So I have a pre-trained language model that tells me that the likelihood of, let's say in my vocabulary I just have at this point 2 words, which is cold and warm. So it says that the likelihood of the next token being cold is 0.05 and warm is 0.10. Now this model has no information regarding the constraint, right? It's not incorporating the constraint in any way. So, but if you look at it, if I want to generate a sentence that contains winter and the prefix so far is the weather is, then it's more likely that the next word would be cold rather than warm, right? But my language model doesn't have any constraints to enforce this. So what instead I can do is I can train a tractable probabilistic model that is an approximation for my language model. Need not be a good approximation, but it is efficient. It can do marginal inference, right? It knows that if I want to generate a sentence that contains winter, I'm actually marginalizing out over, I'm computing this likelihood over your constraint given what you have generated as a marginalization task. And it knows that the likelihood of the next word being cold is going to be much larger since you want to incorporate the constraint that the sentence should have winter. Right? So it knows that knowledge, and the way we defined it, you are taking a product distribution between your pre-trained language model and the tractable model. So as a result, what you get is that you generate a sample in which so for example here the likelihood of generating cold is larger than generating warm, right? So this is just an example. This is not always true. You could always have other like sentences in which the order is flipped and things like that. But to give you the picture, you have the high level idea, right? You have a generative model, a deep generative model that cannot do marginalization, and it's not easy for it to satisfy constraints, hard constraints. What you can do is you can use a tractable probabilistic model to guide the generative process of this, and the way that you do it is by taking a product distribution in which one term gives you the likelihood of it generating or satisfying the constraint, and the second term is the likelihood of your deep generative model generating the sentence itself, right? So what you get is, there's a whole benchmark called common gen dataset in which you have constraints like this, that you want to generate data that contains or sentences that contain certain words. And what you observe is that when you compare it with state of the art language generation methods, you can see that this particular framework Gelato always results in 100% satisfaction of all the constraints that you have, and it does so without resulting in any loss of performance. In fact, it has better performance than some of these models, right? So the whole point is you can use the tractability of a probabilistic circuit or models of this class to guide to better do the generative process in deep generative models. So that is like one application that is like people are have been explored and like that are that's very hot. So this was for generative models with language, but you can also do the same for diffusion, as I was saying. Any questions on this? Yeah. Mm-hmm. This one or previous?
So basically the PC that is going to minimize the k and divergence.
Mm-hmm.
So what kind of training data is required for training?
So you're interested in building a PC that is a good approximation to your deep model. So what you do is you generate samples from your deep model, right? And you train a PC over the data that you have generated from a deep model, so that the distribution that the PC learned would be close to the distribution that the deep model has learned. Yeah. So I had some slides on how you do that. There's an entire paper on distilling the knowledge from a deep model to a tractable probabilistic circuit. I have references in the slides, but due to lack of time, I don't think I'll be able to go through it. Yeah. Yeah. So here, the thing is, when you have a tractable circuit, the likelihood of a sentence in which the constraint is violated would always be 0. So when you are taking the product, that likelihood goes to 0, so you won't generate it. So it will guarantee, in fact. And like the thing is, for different types of constraints, you will have to have different probabilistic queries. So here it's just marginalization because you're only interested in looking if that particular word occurs somewhere. Now you can have more complex constraints which says, okay, I want the second word to be something, the third word to be something else, and things like that, right? Or like the example I discussed earlier, where you want a particular ordering, right? But all of those can still be compiled into a circuit, right, which always satisfies that constraint. Yeah. Yeah. Einsum differs from convolutions. So what an einsum does, a convolution will preserve your, it has the translation invariance, right? It's more like a feed-forward neural network at a convolution layer, but with shared weights. That's what a convolution does, right? In einsum, you don't really have any such weight sharing or that ensures that you have any sort of translation invariance. It's just taking products and summing over some axis, right? But I don't know, can you think of einsum operations as convolutions? Maybe it depends on how you define the einsum. There might be, if you are defining over different, if you're taking the summations over axis, but you have shared weights along the axis, then it might be equivalent to doing convolutions. I'm not sure, but that would be nice to think. Yeah. Yeah.
How does this handle when there do not exist probabilities of the conditions that we're giving? How does it handle those kind of things?
There do not exist the probabilities of conditions.
So if we are giving a few words, those words don't exist in our training set.
Oh no, so you have the assumption that you have a fixed set of vocabulary, right? So whatever so that's always the case with any like language model. Your vocabulary is fixed, so you can have like 50,000 words or like 100,000 words, but that is fixed. So whatever you're generating, even the constraints that you have should also be from the same set, right? Right. Yeah. Any more questions on this? Yeah.
Data vanishing is affect these overall PC.
Data vanishing.
Data vanishing will happen, right, when we are taking the training data from the deep models.
So you mean if the deep model doesn't model your true distribution, there are regions in your distribution that, let's say, long tails or something, where your deep model is not generating data from, and you're training a PC, the PC will also not generate data from the same region. Right? Is that what you're referring to? Yeah. So that's okay, because we are not our objective is not to train the deep model to do better sampling. Our objective is to make the generative process satisfy the constraint, right? So as long as your PC is a good approximation for whatever your deep model has learned, right, that's all we need for this formulation. Now you can actually think of going a step further and training everything end to end, where you also train the deep model using the feedback coming in from the PC, and ensure that long tails are captured somehow. But that's not the point here. The point here is you have a fixed learned deep model. It can be good, it can be bad, right? It can have generate samples, it can have what is called mode collapse, where you don't generate from all regions in your distribution. But it is a model, and what you're really interested in doing is constraining the generative process of this model. Whatever it generates, you really want to ensure that certain constraints are satisfied, right? So you need an approximate model, which is tractable. So you train that by generating samples from this deep model. If the deep model has mode collapse, you'll also expect the PC to have mode collapse, right? But for the PC, it's only interested in learning what distribution the deep model has learned. It doesn't really matter what the real distribution is, right?
Okay.
For this constraint generation task.
Yes. Here another thing is like when this deep model is training the data that we have,
Mm-hmm.
whether it is a diverse data or one specific to one region,
Mm-hmm.
there is a it will encounter the data vanishing, right? Most probably. Like we are giving 100 words, it will train for only 99 words and maybe semantic accessibility different those kind of things, right?
That can happen. There could be like pathologies in the training of deep language models, and how do you overcome that? That would be a research question in the like large language modeling literature, right? But I'm not an expert in large language models. But yeah, but my point was to like show you how you can use the tractability part, right? Even in deep models to get constrained satisfaction, constrained text generation. Make sense? Yeah. Good. Okay, let me see if I can quickly go over one more application that we work on. That is in the context of multimodal fusion. So the way we reason as human beings, like we utilize several modalities of information, right? So we have the images of the world coming into our eyes, we hear things, we can smell things, right? So these are all different modalities of data that our sensors provide us, right? Our human sensors provide us, right? And we make a decision by combining the information that is present in each of these modalities, right? Now, when you build an AI system in the real world, typically so if you really want to build a robot, you'll also encounter the same situation where you have multiple modalities of data coming in, right? You'll have videos, you'll have audio, you'll have other sensor data, right? And the best way to make a decision is by combining the information that is present in all of these modalities, right? So that is what the field of multimodal fusion looks like, or like deals with, where you come up with architectures and learning algorithms that can fuse the information present in different modalities to make a particular decision, right? So the context is that we want to utilize all modalities of data available to learn any given target concept. I'm just going to look at a discriminative learning task in this case. But what can happen in many real life applications is that your modalities can offer complementary information, and to get a better view of the world, you need to combine everything, all the information, to have a comprehensive understanding and better predictive performance, right? So let's try to ground this in an example. Let's say you are interested in predicting the likelihood of having a heart attack. So that is your target concept. You have a lot of risk factors associated, which are your features that could contribute to heart attack. Now, each of these could be from different modalities themselves. So for example, you could have physical symptoms, which can be written down. You can have features coming in from lab tests. You can have MRI scan images, etc. So each of these are a different representation of data, a different modality, and each of them provides you some belief about whether you will have heart attack or not, right? So if you look at the conditional distribution over Y, given each of these modality, you will have some notion of having a heart attack. But what can happen typically is that there's always noise associated in your system. There's noise in your data, there's noise in your sensors, there's noise in your machines, right? So in such a setting, what happens is each of these modalities can give you conflicting notion of your target concept. So for example, my physical symptoms can say that, okay, I'm most likely to have a heart attack, right? That's most likely what Google tells you if you like search for some diagnosis, right? That, okay, I'm having a headache, and like you go through Google, and at the end of the day, you're like, oh my God, I'm having something serious. But if you really take another modality, let's say for example lab test results, it could say that no, you're fine, you don't have to do anything, right? So in such settings where you have modalities of information that is suggesting things that are conflicting about a target concept, how do you combine these data in a sound, reasonable way, right? So there's uncertainty here definitely, and you can sort of like I can hint that we are going more towards taking a probabilistic view where we want to fit a probabilistic generative model over this unimodal predictions. Right? So, and the thing is, we are not just interested in combining these predictions. We need to do it in a way that enables us to infer how credible a particular modality was, right? How much information, how much credible is the information coming in from a particular modality is, so that you can decide whether you can trust that modality. How much can I trust this particular decision? Do I need to discard a particular modality if it's too faulty, right? So that it doesn't affect the final decision that I make. So there are a lot of cases in which when you are doing multimodal fusion, you need a way of assessing credibility of the information that is present. And this was actually a project that came in that was funded by a grant that we had, in which we had it's from the Air Force Research. So they had an application in which you actually have data coming in from multiple sensors, and you need to make sure that the information is credible. So how do you do that in a probabilistic way? But before that, let me just tell you what the process or what the task we have looks like, right? So you have data which are coming in from different modalities. Let me call x1 up to xm as different modalities of data, and you have experts that are trained on each modality, right? So it's more like the medical setting where I'm saying that, okay, the MRI images tells me that I have a risk of heart attack, for example. So you're making a prediction, you're trying to decide what the target concept would be based on each individual modality. So it's more like you have a classifier for each modality that outputs the distribution over your target concept given that modality. And then you want to combine these distribution using some fusion function, right, in such a way that you can make good decisions, and you can also infer some notion of how credible a particular modality was. So what people have typically looked at is in using things like weighted average, noisy, or even MLP and neural models as this fusion function. But the thing is, while simple models like weighted average and noisy are, they can give you some notion of importance and credibility of a particular modality, they are not really as expressive as neural transformations. And neural transformations, though expressive, it's very hard to, they are like black box models, right? You cannot infer any notion of importance, credibility from such a neural model. So what we are interested in doing is, we are interested in building a class of, or interested in using probabilistic circuits somehow to define a notion of credibility here and use it as a fusion function in this context, right? And the way we do it is, okay, if I were to take a probabilistic view, I have uncertainty that is associated with each target that I'm predicting from each modality, right? So I have y given x1, I have a distribution over y given x1, right? But there is always uncertainty over it. So I have a distribution over these unimodal predictive distributions themselves, a joint distribution. What if I can define the credibility of a modality as the relative amount of information that each unimodal predictors provides to my final prediction. I'll define this, right? So let's say I have a joint model over P1 up to Pm. So P1 up to Pm are the unimodal predictors, and I have a joint probability distribution over these random variables. I can define the credibility of a particular modality as the divergence between two distributions. So I'm looking at the final prediction given I have all the unimodal predictive distributions P1 to M, and suppose I were to remove a particular modality. If I were to remove a particular modality, then and my decision changes by a lot, then that means that particular modality is very important in making that particular decision, right? So it's more like formulating how important is the unimodal distribution of a particular modality in your final decision process, but everything in a probabilistic way, right? And if you really look at what this involves, you are computing the divergence between two distributions. One is the joint, but one is a marginal distribution. You are marginalizing out one particular modality and looking at how your decision changes based on that, right? So clearly you need some sort of tractable model here to do marginalization, and that can help define your notion of credibility, right? So what we will do is we'll just use a probabilistic circuit. So you'll fit a probabilistic circuit over your unimodal distributions themselves. So it's a distribution over distributions, right? But a probabilistic circuit is also expressive. You can make it deep. It can model arbitrarily complex interactions between these unimodal predictors, and it can fuse the unimodal predictors effectively. Right. So we have two papers in this direction. One is under review. One is accepted to fusion. But that's the key point, right? So when you're defining such notions of credibility from a probabilistic standpoint, queries like tractable, probabilistic queries like doing conditioning and marginal inference becomes important. Right? They can be useful in defining such things, and having a tractable model that can perform marginalization and conditionals can help in such applications, right? So the key is, again, identifying what tasks that you have at hand requires tractable inference. That itself is a problem, right? So identifying where tractable inference can help in the applications that you are working on, and then using an expressive model that can do that is tractable for that particular class of queries you need, is sort of like the way like how you adapt probabilistic circuits for the applications that you have, right? But again, this is just one more example of how you use probabilistic circuits for in the context of multimodal fusion. Talking of some results, what you get is, since your PC is expressive, you get performance that is similar to having a neural model, right? So let's say this is fusion with a neural model. Here is, these are both like probabilistic circuit based fusion methods. So you get performance in terms of accuracy, precision, etc., that is similar to neural models, but at the same time you have a way of evaluating credibility, right? So the way we evaluated credibility was take a particular modality, keep on adding noise to it until it becomes completely random noise, right? And when you do that, the credibility of that particular modality should decrease, right? So what we like experimentally observed was, if you were to incorporate noise into the image modality here, and you look at the credibility scores that the PC computes, as you increase the noise present in that particular modality, the model is able to say that that particular modality is less credible, right? And having a probabilistic model also has other benefits as the combination function. We had some extended analysis showing that taking a probabilistic view makes the model much more robust when you have out of distribution data, when you have noise in your data distribution, and it also helps produce neural models which are more calibrated, which can be like reliable. So, so do you guys know what calibration means? Okay. So when you say that a model is calibrated, if the likelihood that it outputs about a particular like decision, so if you have a classifier and your neural model is saying that the target is going to be, let's say, a cat with likelihood 0.6, right? Then the accuracy, if you were to classify, let's say, 100 examples, would also be 0.6, right? So the accuracy that the classifier has on a test distribution matches the likelihood that it outputs, right? So if your accuracy does not match the confidence, you can have models that are either overconfident or underconfident, in which case they are not calibrated. But having a probabilistic circuit as your fusion function in multimodal fusion, implicitly, without having any additional regularizations or additional loss functions, it makes it much more calibrated and reliable. So those were just two applications of like how you can use these tractable models in some real world settings. But this is not exhaustive, right? I have a bunch of references at the end about how people have used PCs in other contexts. But if you have any questions regarding this, I think I'll take it now before I conclude in like another 5 minutes. Any questions? Yeah.
We were looking at the importance of a modality by
Mm-hmm.
trying to marginalize it by
Right. Right.
wouldn't principal component analysis
Principal component analysis in what space? So you're looking at the space of distributions over your unimodal predictors. So you have experts over each modality, right? So you have distributions over your target concept given each modality, right? And you're combining it with a fusion function. So I think what you're saying is, if you have a neural model somehow, then you could come up with some notion of how important a particular modality was by doing principal component or looking at eigenvalues of this transformation. But it would still be expensive. If you have a neural model, right, you'll have to compute. So you'll have to do something like a singular value decomposition, compute the eigenvalues and stuff. So doing that is computationally expensive, right? Plus, I don't think you have any sort of probabilistic guarantees that you can get when you have a tractable model in that case. Because there are also other ways you can do. The whole field of explainable AI has looked at things like feature importance, how important, like gradient-based explanations, GradCam and stuff, which can also be used to like come up with how important was a particular feature for making a particular output, right? If you have a neural model, but then again, those are not very grounded in any sort of probabilistic reasoning or framework, right? Yeah. Yeah.
When you're doing this credibility aware
Mm-hmm.
finding of these features,
Mm-hmm.
so are you bringing the true label into the picture, or you're just looking at that difference that the predicted distribution has when we just remove the
Mm-hmm.
feature, or we are doing that, or we are also bringing in the true label?
No, we are not. So we are just looking at the how the distribution shifts.
The predicted distribution.
Right, how the predicted distribution shifts. Right. You could also incorporate the true label, but that would be more of a performance score than a credibility score. Right.
So in that case, is it like credibility is similar to having feature importance, calculating feature importance?
In some way, yes. In some way, but it's a more probabilistic way of doing this. Right. Yeah. Because you can also do this. So for each given data point, your the credibility could vary. Right? So for a particular data point, one modality could be more important or more noisy than the other modalities, right? So the credibility of a modality can vary for each data point, but you can also look at a global scale over the modality itself. At a global scale, which modality is most important? So you can define credibility at local data point level and also at a global level, right? Again, similar to what you do in feature importances. You have local feature importances and global feature importances. Yep. All right, so that was a lot of content in 3 days, right? But what I really want you to take away from this workshop is that there is this field of tractable probabilistic inference which is underlooked in recent days, where deep models have taken over. But this is a powerful class of models that, having tractability for probabilistic inference allows you to perform complex reasoning over data effectively, especially when you have uncertainty. It can do things like handling missing data, making decisions that are robust and interpretable. You can marginalize out effects of things like sensitive features, especially when you want to ensure fairness, right? So let's say you have a classifier that is trained to decide on, let's say, who gets approved for a loan, right? And you have features that are sensitive, let's say things like gender, right? So you want to ensure that the decisions that you make are not do not contain any sort of bias, and it is fair. And one probabilistic way of doing such things would be to marginalize out those the effect of those variables from your decision, right? So those things require you to do tractable probabilistic inference, right? And at a very high level, we saw that if you take a view of the generative models out there, the generative modeling landscape, you will see that there are classes of models that are very expressive, like deep models, right? But they cannot do tractable inference. They cannot do probabilistic reasoning, but they are very expressive. They can generate very good quality samples. So if the application you are working on requires just generating samples, that's what I would go with, right? But on the other hand, you have this more tractable class of models which have a lot of structure in them. They are not as expressive as your deep models, but they can do certain types of probabilistic reasoning, which also might be important in certain applications, right? And the whole context, or the whole idea behind this workshop and the research that I work on is how do you build classes of generative models that can achieve best of both worlds, right? So you need tractable models, you need tractability for inference, but you also need them to be expressive and capable of approximating complex distributions. And we saw two things, right? So what we saw yesterday was that we take these classic simple tractable distributions, we take mixtures over them, we come up with a representation that is compact, that can be easily vectorized and scaled to millions of parameters, which we call probabilistic circuits, right? So I took these classes of models, defined mixtures to get models that are more tractable, more expressive, called probabilistic circuits. What we also saw today was how you can bring concepts from these deep modeling side, especially like normalizing flows, and incorporate it into these probabilistic circuits to improve their expressivity. And what we saw was that when you do that, you will also have to ensure that there is some structural properties that you are enforcing on these hybrid models, right? So that's like a very high level picture. And what is a probabilistic circuits? Again, if you if you go back from tomorrow's work from the workshop today, what I really want you to like keep in mind is that there is this class of probabilistic circuits which are similar to neural models in terms of being computational graphs, but they are computational graphs defined over probability distributions themselves. They can be used to approximate complex distribution, right? And it utilizes the two notions of factorizations and mixtures. Factorizations help you achieve tractability for inference. Mixtures add expressivity to your model, right? And that is probabilistic circuit. And when you define structural properties over these probabilistic circuits, you can make them tractable for different classes of queries that you're interested in, right? We just saw like 4 classes of queries, but you can come up with arbitrary queries that are important for your task. It's defining some operation over your joint distribution, and you can see if the model is, you can check if the model is tractable. If it's not tractable, what structural properties can you add to make it tractable? Those are some of the research directions that people are looking at right now. Now again, if you have such a class of models which are expressive and tractable, they can benefit a lot of domains. So we saw how it can benefit control generation very briefly. What you can also do is do NeuroSymbolic learning, where you can incorporate these probabilistic circuits as a layer in your neural models, but as a constraint satisfaction layer, right? So there's work that does this. Satisfying constraints in the output of a neural model. There are also works that looks at knowledge graph embeddings, how you can scale knowledge graph embeddings and convert knowledge graph themselves into a generative model using probabilistic circuits. This is just to tease you on the applications and the things that people have done, so that if you're interested in any of these, you always have the references to go check them out. You have things like image painting, where you can generate occlusions. You can look at conditional distributions over occlusions. People have used it for speech reconstruction, for semantic segmentation. Semantic segmentation is more like a map problem, right? You can pose it as a map problem from a probabilistic standpoint. You can also think of things like scene understanding, robotics and routing, where you are interested in reasoning about certain subsets or certain subspaces in your data space. You're interested in what is happening in a particular region, which typically involves marginalizing out the rest of the content in your scene. It's also very common in robotics and routing. So in such applications, there is value for probabilistic inference, tractable probabilistic inference, and these classes of models can benefit such applications. Right? So with that, I'll end the session, but I'll open it up for questions. Any questions?